טוב, בוקר טוב לכולם. הגיעו הבוקר רק 6 אנשים בינתיים, אז אולי נחכה עוד 2 דקות ואז נתחיל. Okay. Good morning, everybody. Let's get started. So we're changing topic today. So this is, where's this? Right. So this is lecture number 8, and I've copied. Oh, I haven't shared my screen. I'm sorry. Let me share my screen. Just a moment. Sorry about this. Okay. So presumably you can all see my screen. So we're going to be changing topics today. So let me remind you, I said very briefly at the end of the previous lecture what our next goal is. So this is where are we heading now? We're trying to discuss constructions of optimal lattice packings or lower bounds on the optimal lattice packing density. So let me remind you what that is. So what is the optimal lattice packing by Euclidean balls in Rn? So this is this number that we called delta n, and it's the max or the sup. We now, it's a priori it's a max, but we also know that it's a sup, and this is the volume of B, where B is a ball. And there exists a lattice of covolume 1 such that the translates of B by elements of this lattice are disjoint. Okay, so we're trying to fill up the maximal proportion of the volume of space possible by Euclidean balls which are packed, which are disjoint from each other. So this fact that we're working in covolume lattices of covolume 1 means that we don't have to normalize this volume by the covolume of the lattice. The volume of this ball divided by the covolume of the lattice, which in this case is 1, is just the proportion of space that this disjoint system of balls occupies. So this is the packing density of a lattice, which we're maximizing over all lattices for the Euclidean ball. Okay? And this is an unknown quantity, so this is known only in dimensions between 1 and 8 and 24. So we discussed this, and the technique for the classical technique for trying to figure out this number is the technique of Voronoi and Korkin-Zolotarev, which we discussed over the previous 2 weeks, and it just fails in large dimensions. And so I'll just remind you that there's some equivalent ways of trying to understand this. So equivalently, we don't know or want to understand. These are just two different ways of getting at the same notion. The max of the shortest lattice vector, the length of the shortest lattice vector over all lattices in Rn, or lattice in Rn of covolume 1, or the max of the same quantity squared over all lattices of covolume 1. These are just, oops, they're easy formulas relating each of these numbers, and maximizing any of them is equivalent. And this last one here is maybe the classical one. This is called the Hermite constant in dimension n. So finding the Hermite constant is the same as finding the optimal lattice packing density, or the same as finding this this best most optimal the longest possible shortest vector in a lattice of covolume 1 in dimension n. Okay, any questions about this? So this is like the classical question that we're discussing. Let's introduce kind of a convenient normalization. So definite notation, R EFF, EFF stands for R effective, the effective radius. This is a number that depends on n, so sometimes I'll put an n on top, is the value of R for which the volume of the ball of radius R is 1, the Euclidean ball. So this is this number can be, so I'll write it differently. So if Vn is the volume of the ball of radius 1 in Rn, then we're choosing Rn so that when we rescale the ball by R, we multiply its volume by R to the n. We're supposed to get 1. So this happens if and only if R is Vn to the minus 1 over n. And then there are some known bounds for this, or known expressions for this volume of the ball of radius 1 in Rn, and they give us that this effective radius grows like square root of n times the constant. The constant is 1 over the square root of 2 pi e. Okay, so this is R effective. Okay, so there's a little computation which is not so simple to do, but it's classical, computing the growth rate of the volume of a ball of radius n. It's sort of an inductive argument, and the volume of the ball of radius n is expressed using gamma functions, and then you use Stirling formula for the gamma functions, and you come up with this kind of an asymptotic. And the theorem that we're going to be discussing goes under the name of the Minkowski-Lavka theorem. It has a long history, which I will explain later. And it shows the following thing. For any n, there's a lattice of covolume 1 whose shortest non-zero lattice vector has length, at least this value R effective radius. Okay, so this is giving us a lower bound on the length of the shortest lattice vector over the lattice for which this shortest vector is as long as possible. Okay, so if you look at this, if you think about Zn, which you might sort of naively think is a pretty typical or a pretty good lattice in terms of not having exceedingly short vectors, you see that that's very naive because the best lattice has shortest vector of length R effective, which is of size square root of n times a constant. So for large n, and Zn has its shortest lattice vector of length 1. So for large n, Zn is actually a very atypical lattice. Its shortest, well, okay, there's something I'm sort of hiding and not telling you. We're going to see not only is this bound attainable, but this bound is also typical for most lattices, and I'll explain what I mean by typical. Okay, so this is the important Minkowski-Lavka result or theorem. Let me say a few remarks about this. So equivalently, delta n is bounded below by 1 over 2 to the n. Why is this equivalent? Well, this is equivalent because lambda 1 of L bigger than this number is the same as saying that, or implies, let's put it this way, implies that the balls L plus B, where B is a ball of radius half of R effective, are disjoint. Let me clean this up a little bit. L over B, L and L. Okay, if the shortest vector in your lattice has length at least some number, then if you divide that number by 2, two balls centered lattice points whose radius is the length of the shortest vector divided by 2 can't intersect each other. If they did, you would get a contradiction to the triangle inequality. So when you have this bound, it implies that these balls are disjoint. Now, what's the volume of these balls? If the radius was exactly R effective, the volume would be 1. We're dividing R effective by 2, so the volume is 1 over 2 to the n. Okay, so I'll write that down. So the volume of this ball and the volume of the ball of radius R effective is 1. That's the definition of R effective. So that's why this is another way, this statement over here, sorry, this gives us just another way to formulate the Minkowski-Lavka theorem. Let me say a few words about this bound. So remarks. Currently best known. I've already said this in a previous lecture, but I'll repeat it because it's important. So delta n is bounded above and below. Below, it's bounded by a constant times n over 2 to the n. And above, it's bounded by something like 0.67 to the n. So this left-hand side, many people are involved, many contributions. Best value of C is due to Venkatesh in 2012. So this is an ongoing, still very active area of research. Well, not very active, but there's been a lot of work throughout. And you see, what do you see from this? Look, what we're going to be proving is this bound, 1 over 2 to the n. And the best known bound is, okay, this is very, very close to 1 over 2 to the n. We're only improving it by a factor of n and a constant. And the contribution, Venkatesh is a Fields medalist for one of the recent Fields medalist awardees. His whole contribution was just to improve the value of the constant here. And on the other side, the upper bound, oops, I'm sorry. The upper bound is much, much larger, 0.67 to the n. This is like half to the n, and this is like 2/3 to the n. And this is due to Kobatiansky and Levenstein. Levenstein from the 70s, and it hasn't been improved for almost for 50 years, essentially. Okay, so this is, you see that there's this huge gap here, and this is a very central problem, is to close this gap. So that's about the current state of affairs. Second remark that I want to make is about the history of this and why is it called Minkowski-Lavka. So Minkowski stated this without proof in 1911, this bound. Then it was proved by Lavka in 43. Lavka is a very well-known Austrian mathematician who did a lot of things in geometry of numbers. And then it was reproved by Siegel in 45. And the proof of Siegel is the proof that we're going to be discussing. It's a beautiful proof. And Siegel claims, and I don't know the history that well, but he claims, so let's just write apparently, filling in the details of Minkowski's argument. So apparently the argument that we're going to be giving was sort of envisioned by Minkowski, and people sort of knew that this is what Minkowski had in mind, but he never wrote it down, and Siegel wrote down the, filled in the gaps. And the third thing I want to say is that this is a probabilistic argument. Proves existence, but there's no explicit lattices with giving us this packing density, or let's just write it this way, with shortest lattice vector greater than R effective, or no. Okay, so what the argument will show, as I said, what the argument will show is not only does there exist a lattice satisfying this bound, but there's going to be a kind of a way of choosing a random lattice, and most random lattice, or a positive proportion of random lattices, will be proved to have this property, but I won't show you any specific such lattice. And I'm explaining that it's a separate problem, and it's currently open to explicitly write down a basis of a lattice satisfying this kind of a bound. So that's an open problem. Okay, so the way the proof goes is via something called the Siegel summation formula. So I'll write, this is the main theorem. So I'll call it theorem A, and then it's going to be called the Siegel summation formula. And this is from 1945, this famous 1945 paper. And it says the following. There's a measure. I'm going to call this measure M of the space of lattices of dimension n, so mxn, on space of lattices, which is, well, it's SLNR invariant. I'll explain everything in a second. 2, it's a probability measure. It's a Borel probability measure. A regular Borel probability. Well, actually, let me say the same thing in a slightly different order. So it's, I'll put the stuff about being regular and Borel in the first item. because I want to emphasize here that it's a probability measure. So it's a probability measure. And 3 is something called the SSF, the Siegel summation formula, and it says the following: for every function of any L1 function on Rn with respect to Lebesgue measure, we have the following thing. We define a function f hat on the space of lattices. We define it as follows. We sum the original function at all non-zero lattice points. And so this function is, function f hat is well defined. I'll explain what I mean by well defined. And it satisfies that the integral of f hat on the space of lattices with respect to the measure, probability measure that we're discussing, is equal to the integral on Rn of the original function with respect to the Euclidean volume. So this is the Siegel summation formula. Now let me back up and explain this piece by piece. And so first of all, notation. So measures, in a usual measure theory course, people use the letters mu or nu for measures. And there's a kind of, in this field, there's a kind of a convention that if a measure is particularly nice or has nice properties or is particularly natural, it gets associated with the letter M, which is kind of a more familiar letter, baby, and the name of the space. So this is, you should think of this measure as in some sense being the canonical or the best or the most natural measure on this space Xn, and I'm going to have to explain to you why that's a correct thing to think about. So what are its properties? So first of all, it's a Borel regular measure. I'll review what all that means in a few minutes. And it's SLNR invariant. Remember that SLNR is the group of n by n matrices of determinant 1, and it acts on the space of lattices by linear transformations. Linear transformations act on Rn, so they map lattices to lattices. And so this measure is invariant for that action. That's the main reason we think of it as being a very natural measure, because it's the group SLNR acts transitively on this space. So every two lattices are related by an element of SLNR, and applying this action preserves the measure. If you want kind of a reference point, think of when you study Lebesgue integration, one of the first properties of the Lebesgue measure that you hear about is that it's invariant under translation. So this is sort of the analog. It's the only measure on Xn which is invariant under the action of SLNR. And then it satisfies this Siegel summation formula. So what is the Siegel summation formula? Starting with a function on Rn, and I'm sorry, one more thing about names of measures. Vol is the notation that we're using for Lebesgue measure on Rn, okay? It depends on n, but I'll suppress the dependence on n. So for any n, Vol is the notation for the Lebesgue measure on Rn. Okay, so I'm starting with a function on Rn, real valued, and then I'm defining a new function on the space of lattices. It takes a lattice, and the output over a given lattice is this sum. Okay. Well, first thing, I'm claiming that this is well defined. So what does it mean for it to be well defined? Well, you might worry that this is an infinite sum. You might worry that this sum doesn't converge. In fact, it might not converge on some points, but I'm telling you that it converges almost everywhere with respect to this measure. So for almost every L, almost every with respect to this measure, this sum converges. And moreover, the function that you get is integrable. So you can make sense of the integral on the left-hand side. And the integral on the left-hand side equals the integral of the original function f. Okay, so this is the content of what Siegel did in one paper. And one more thing to say, um, in many textbooks, the so statement one is easy, relatively speaking. We're going to be discussing it today. Um, Constructing a measure on such a space, which is SLNR invariant, regular, and Borel, is not so difficult. But making sure that it's a probability measure, or at least a finite measure, that you can find an invariant measure, which is a probability measure, that's more difficult. And you have this complicated formula which makes it possible to evaluate the sum of the integrals with respect to this measure. In most texts, the first step is sort of done from general easy principles. The second step is a more difficult step. It's done separately, and the third step is done separately. In our proof, steps 2 and 3 will be proved in a kind of a induction that involves both statements at the same time. And this is going to take us several meetings. I hope to complete the proof of 2 and 3 next week. It won't happen today. So this is our next goal, and it's going to take a while to do this. But now, what I want to explain is,
Bach, does this
yeah,
does the proof have anything to do with like groups and harm measure? I don't
de
understand these things very well, but
definitely. This is all about, this is exactly the right viewpoint that Siegel was bringing into the picture. It's all about using harm measures to define invariant measures on quotients, and that's what I'm going to be discussing.
okay, thanks.
That's exactly it. And also explain what harm measure means and so on. Okay, so any other questions? Okay, so let's just use these formulas, in particular this. Maybe I should move the letters SSF. SSF, Siegel summation formula, is this formula, this identity between the two integrals. So let's explain why theorem A.
Sorry, Alec, can I
Yeah,
ask?
sure.
Maybe some general formula, but like this, the Siegel summation formula looks kind of reminiscent to Poisson summation. Is the
There's a vague relationship, so it's harder to prove than the Poisson summation formula. There's something in you're going to see during the proof that's called the folding identity, which is kind of a it's even closer to the Poisson summation formula, and it's to the Poisson summation formula, and this folding identity. Um, Well, okay. You'll see more about that in the proof, I hope. Yeah, another thing to say just about notation. This hat, many people are going to object to this hat, but it's sort of entrenched in the literature. So why should people object? Because the hat is also used for the Fourier transform. And the Poisson summation formula is sort of a similar identity, but the hat means a different thing. It means like the Fourier transform of a function. So this does not have to. It's not about the Fourier transform, although it has interesting, sort of interesting interactions with the Fourier transform. I don't know. In some appropriate generality, maybe these are similar objects, but they're somewhat different. Anyway, we're going to be using this hat notation, even though it's somewhat confusing. Okay, let's.
Can I also ask a question?
Sure, absolutely.
Relating to shy questions. So, just historically, what was first? The quotient was isomorphic to the space of lattices, or that they knew that the quotient inherits the Haar measure from the original space.
So this, I don't know how to exactly, I'm not exactly sure. So this uh, paper of Siegel from 45 is very, very influential. And so a lot of these ideas were sort of floating around. I don't think that the quotients of Lie group's point of view was in the literature in the writings of Minkowski. And I don't think that the topology on this, we introduced a kind of a topology on the space of lattices as a quotient using this Chaboty topology, and I also don't think that was in the literature. So that's kind of a more modern point of view. So I actually don't completely know the answer. So the Mahler compactness criterion comes before this Siegel summation formula, the Mahler compactness criterion we discussed last time. And so it's more like a topological thing on the space of lattices. But that was also written in a different language. So I don't know. Short answer is I don't really know. This is kind of crystallizing in this form, let's say over the past 40 or 50 years. A very influential figure in this whole development is Andre Weil. Andre Weil, many of you have probably heard of Andre Weil, and he had a kind of a very he was one of the early Bourbaki people, and he had a kind of a abstract axiomatic point of view on many branches of mathematics, and he had a huge influence on this topic because he axiomatized a lot of the ideas in the language of groups and Haar measures and quotients. And so his influence is in the background here. And but I don't know about the original history. Okay, that's what I think about the history, but I'm not an expert on this history. Okay, other questions? All right. So I'm going to now just use this Siegel summation formula as a black box so that you see how we prove this bound. Where did this go? This Minkowski-Lavka theorem, this theorem. Why does there exist a lattice satisfying this bound? Let's prove that, assuming we know this uh, this theorem, theorem A. So proof of Minkowski-Lavka, assuming theorem A. So suppose theorem A is, suppose Minkowski-Lavka is false. So what does that mean? For every lattice in Rn, the length of the shortest vector in this lattice is less than R effective. Okay, remember R effective depends on n. I'm just not putting that into the definition. So what does this mean? What does this mean? This means that if I intersect any lattice for all L, if I intersect the lattice L with the ball of this radius, I'm going to see non-zero vectors because it's not true. Yeah, because of this. It's not true that, I mean, the shortest lattice vector is shorter than this R effective, so this ball had better contain lattice points. So that's what we get. So this means that this ball contains at least two non-zero vectors plus minus v, right? Well, as soon as we have one, we actually have two because the minus of it is also in the ball. So now let's take the function f, which is the indicator of the ball of radius R effective. By the Siegel summation formula, the integral of this function over Rn is 1 because, well, let's write another line here just so it's absolutely clear. So this is the volume. The definition of R effective means that the volume of this ball is 1, and this is the integral over Rn of this indicator function. But this is the same by the Siegel summation formula as the integral of f hat. And what do we know about f hat? This is the definition of f hat. but the ball intersect the lattice contains at least 2 points by what we just said. So we have at least 2 non-zero vectors. So this sum has at least 2 non-zero contributions for any lattice. So this is at least 2. So we get here this, all of this implies this, and we get our contradiction. All right. Let's think about this proof for a moment. What did we use? We were being a little bit wasteful with some bounds, so let's just record that. So there's several things to record about this proof because it's kind of a very standard proof that we should get used to. So, well, we get the contradiction that we got is 1 is bigger than 2. And as I said, it seems kind of strange now, maybe to you, but people are really interested in these lattice constants. So even this tiny bit of waste, maybe people want to record it. So we could have done just a tiny bit better and gotten a constant, a little tiny constant improvement in the Minkowski-Lavka theorem if we had done this more optimally to make this say 1 plus delta or something like this. So let's just write that down. So can improve constant very slightly by replacing, well, you can't replace, sorry, you can't replace the right-hand side. So you can't really change this 2 because it's an integer, it's the number of points in the ball, but maybe you can change this 1 just a little bit. Take a ball which is just a little bit bigger and make this a little bit bigger. So by replacing 1 on the left-hand side with 2 minus delta for some delta positive. Another thing to say is that if basically what we're showing is that if we have a subset of Rn measurable, it doesn't really matter that this is a Euclidean ball, then there exists a lattice of covolume 1 which intersects it. So sorry, I want the volume of A to be less than 1. And the argument will show that I can find a lattice, sorry, I can find a lattice which misses this ball. Okay, basically what are we doing? We're taking this, we're arguing by contradiction, and the contradiction assumption is that we can, the contradiction assumption is that this ball always is never disjoint from the lattice. Okay, that was our contradiction assumption. This means that this ball is never disjoint from the lattice except for at the point 0. And this leads to a contradiction. So if you use the same argument, you can prove what I just wrote down. Take any measurable set of volume smaller than 1, then you can find a lattice with this property. And as I said earlier, not only does the argument show that there's a lattice, if you slightly change the numbers here, you're going to, in order for, where did this go? In order for these two integrals because this is an integral on the right-hand side, you can get estimates on the measure of the set of lattices for which this holds if the gap between these numbers is large enough. So this is something we're going to be discussing in more detail. Okay, so that's this is a kind of a very simple argument deriving the Minkowski-Lavka theorem from the Siegel theorem A. Questions about this? Okay, so what's our plan now? Let me just bring up the Ziegler summation formula. So I don't know exactly what to assume about this audience in terms of background in measure theory and in topology. So there's a kind of a middle way, which is the way usually chosen in advanced courses, which is to say you assume nothing, and then to just very quickly rush through some kind of reminder, something that's called a reminder. And it often contains lots and lots of new information for most people. So that's what we're going to do. So I'm going to remind you of things that you supposedly think that you already know, and hopefully confuse you enough to force you to think about what you know and learn, learn a little bit more about it. And so this is a kind of a reminder about measure theory. And along the way, we're going to be discussing actions of groups on spaces and how they interact with measure theory, because that's really what's important here. All right, so this is like a reminder with double brackets about measure theory. And since people may want to, some of you may know a lot of this stuff and some people may not, so let me just say briefly what it is I'm going to cover. So besides the basics, I'm going to talk about the Riesz representation theorem, which is something that's often skipped in the course on measure theory, and it's going to be very, very important for us. So I'm going to spend some time discussing the Riesz representation theorem. I'm going to be discussing Haar measures and more generally invariant measures for group actions on spaces. And I think that's going to occupy the rest of today's lecture. We'll see, maybe there will be time to sort of move in closer to theorem A. I'm going to do this a little bit quickly, but this is for you, so don't hesitate. There are only 13 people here, so please stop me if you'd like more information about anything I'm talking about. So in general, when you study measure theory, you start with a set and a sigma algebra. So just to recall, a sigma algebra is a collection of subsets of X, which is closed under countable unions and intersections, and also under complements, and also contains the empty set and the entire set. And then a measure is a function which is defined on the sigma algebra and takes non-negative values. And you see that I'm allowing it to take infinity as a value. So you have to sort of, it's going to be important for us to discuss this situation where the measure is potentially infinite. So we're not only going to be discussing probability measures. So infinity is allowed. So whenever you talk about sums and et cetera, you have to figure out what I mean by summing the symbol infinity. It means what it should mean in these contexts. And so this has the properties that, how does this go? The measure of a countable disjoint union is the sum of the measures. And this already implies monotonicity, so, oops, and many other properties. So this is the basics of what's called a measure in a general situation. But we're going to be caring about, so in general, what I'm trying to emphasize here is that in general, the set X comes at us with no structure at all, and the sigma algebra is sort of given as part of the structure. But the setting that we care about is actually when X has more structure. It's going to be an LCST space, a locally compact second countable space. I'll say something about that. And then B is a sigma algebra that comes from that structure. It's the Borel sigma algebra. So let's write that down. In our setup, X will be locally compact second countable. So most of you have taken so I'm calling that LCSC. So most of you have taken a course in topology, and I don't need to tell you what locally compact second countable is. For those who haven't, I'll just give a special case of without defining LCSC. I'll just tell you a special case, and that's everything that we do in this course will be good enough. A special case, and those of you who have taken the topology course should refresh their memories about why this is really a special case. Special case of LCSC is X is a metric space in which closed balls um, are compact. So this is sometimes called a proper metric space. And so I'm saying that if you don't know what an LCSC space is, it's enough for our course to think about these metric spaces where closed balls are compact. And the main example is the space Xn, which we already equipped with a metric. So it's a metric space. And in the exercise sheet, I've added an exercise asking you to verify, to verify this property that closed balls are compact for this particular metric space. I'm not saying that all LCSC spaces are metric spaces in which closed balls are compact. I'm just saying that this is a kind of a subclass of LCSC spaces, which is big enough for our purposes. And in our setup, B will always be the Borel sigma algebra. So this is the smallest sigma algebra containing the open sets for this metric. Okay. And when you have this topology, you have this notion of compact sets and open sets. You can talk about some regularity properties of the measure, which are sometimes given in kind of a later stage of a standard measure theory course, and that's what I want to focus on. So now we have a triple. So X is a LCSC space. This is the Borel sigma algebra, and this is a measure. And let's give some definitions about this setup that we can give now that we have the topology interacting with the measure theory. So mu is locally finite if for every x there exists a neighborhood u of x such that the measure of u is finite. And in LCSC spaces, this is equivalent to requiring that the measure of compact sets is finite. Why is this equivalent? Well, the implication goes two ways. First of all, suppose you're given this definition, and now I give you a compact set. Every point in the compact set I can cover with a neighborhood satisfying this property. Then I can pass to a finite subcover, and I get that the compact set is contained in a finite union of such open sets, and therefore it has a finite measure. And conversely, if I have this property for convex sets and I have points, then I can just take a ball around this point and its closure is compact, and that's going to play this role. That's for the metric. That's in the setup that we're discussing proper metric spaces. For more general LCSC spaces, that's also easy from the definitions. Okay, again, please stop me if I'm going too fast. So this is the definition of a locally finite measure, mu, the measure mu is called irregular if for any open set U, its measure is the sup of the measure of compact sets contained in U. It's called outer regular if for any set in the Borel sigma algebra, its measure is the inf of the measure of open sets containing S. And an important definition for us, mu is called Redon if it is locally finite, inner and outer regular. And I should have said Borel, locally finite. So a measure is called Borel. I should have said that earlier. B will be the Borel sigma algebra, and then if mu is defined on the Borel sigma algebra, then mu is called Borel. Okay. Let me take a few more minutes and just state the Riesz representation theorem, and then we'll take a break. So let's, I'll write it quickly and then make some comments after the break. So let CC of X be the collection of continuous compactly supported functions on X. And given a measure which is, let's just say Redon measure. I'm going to find a linear functional I sub mu. It's a linear functional on CCX. So it takes functions in CCX and spits out real numbers. And I define it just using integration. And there's quite a few things to say about why this is defined. Let me just say them quickly. So first of all, given a measure, we can integrate. So that's the first thing you do with a measure in a basic course on real functions. So I'm not going to explain what this formula means. This formula is always defined, but it could potentially be infinity, or it might not converge if the space is not, if the measure is not a probability measure, if the space is not compact, or in many situations. But we're working with compactly supported functions, and we're working with a measure which is finite on compact sets. So because of those two facts, this makes sense. So this is a real number. It's not infinity. Okay, so let me just stress that this is a real number. Oh, I've already said it. This is a real number. It's not infinite. Okay, and the Riesz representation theorem says that you can recover the. So I'll write this down. So I mu is a continuous positive linear functional on CCX, and the Riesz representation theorem, so this is called the Riesz representation theorem, and sometimes more names are given. So sometimes this is called the Riesz Kakutani-Markov representation theorem, or some permutation of these names. is often associated with this theorem. Maybe I missed someone. So it says that the mapping that sends radon measures on X to, to continuous positive linear functionals on CCX. By that I mean the mapping that sends the measure mu to the corresponding functional I mu is a bijection. Okay, so this is a central theorem. And after the break, I owe you a few things about this. I need to tell you what positive means. I need to explain this linearity, which you can already, it's what you expect. I need to explain what this continuous means, and this is kind of a slightly subtle point, so I'll spend a few more minutes on this continuity. And also I need to tell you why this is such an important result for us and in general. So let's take, if there are any questions about the statements, except for these definitions, please ask now. Okay, and if not, let's take a 10-minute break and then I'll show this. Okay, so let's continue. Just a moment. Okay, so I want to tell you a few more things about this theorem. So first of all, what do I mean by a linear functional? So this space, I didn't define compactly supported. So compactly supported means functions which are 0 outside of a compact set. And it's clear that if you add two functions which are 0 outside of a compact set, or if you subtract them, or if you multiply them by scalars, you get functions with the same properties. So this is a vector space over the real numbers. So as soon as it's a vector space, we all know what linear functionals means. Positive means positive. So I'm defining the terms in this theorem. So let phi be a linear functional. Phi is called positive if it sends non-negative functions to non-negative numbers. And phi is called continuous if the following holds: for every k in X compact, there exists a positive number C such that if F1, F2 vanish outside of K, so both functions are supported inside K, then the difference between the value of the linear functional on F1 and on F2 is bounded by this constant C times the sup norm of their difference. Actually, I don't need to say this is, I'm saying it in a complicated way. This is enough to work with one function. Sorry. Okay, so this is the notion of a continuous linear functional, and We're interested in this particular linear functional here. So phi is given by this formula, and it's clear from this definition that it satisfies this property if you let C be the measure of K, which we assume to be finite. So clearly, I mu is continuous for each K. Take C to be the measure of K. And again, this is what we want. And where is it? This is the definition. So clearly the value of this integral is less than the maximal value of the function times the measure of the set K on which it's supported. So this is the notion of continuity of a linear functional. And now let me say why this is somewhat confusing. So this is a remark for people who have thought about these things, or may think about these things. So if X is compact, then continuity just means that it's a that phi is a bounded linear functional on C of X, and this is a Banach space with a sup norm. So whenever you have a Banach space, you have a notion of a bounded linear functional. A bounded linear functional is basically the same as a continuous linear functional for Banach spaces. And okay, if you don't know what this is, don't worry about this. This is just a remark for people who've studied these things. And I'm just pointing this out. So if you take this definition of continuity and just apply it for the compact, if X is compact, you can just apply this for K equal to X, and then you find a global constant C satisfying this property, and this is what it means for a functional to be a bounded linear functional. So this is not an this definition is somewhat involved, but it's not really involved in case X is compact. The reason that this is somewhat confusing is that CCX, this space here, is not a Banach space. Okay, if I could try and equip it, for example, with the sup norm. It won't be a complete space. So I'll just give the standard example. So note CCX with sup norm is not complete when X is not compact. For example, I'll just draw a picture and you'll see what I mean. We take X to be the real numbers, or maybe let's take X to be the non-negative real numbers. And let's just draw some functions. And so this is maybe F1 sort of goes like this. F2, this is 1, 1/2, sort of goes like this. So these functions are the FIs take values in 0, 1 over I, and supported on something growing, let's say from 0 to I, for example. And these functions why did I take this example? Just a moment. wait, these functions can converge to the zero function, which is compactly supported. So what did I want to say about this example?
I think
I'm
you
sorry.
don't want to take 1 over I. No?
Just once.
Yeah.
No, but then it won't converge in the soup norm.
Convergence in the soup norm. Okay.
Why did I?
I mean, this is a classic example, I think, for like not converging in L1 norm.
No, I don't care about.
So,
Well, you could, if you want, you can draw a sequence of Gaussians and cut them off.
Right,
you can just
and
draw
then,
a triangle. You can just draw like a triangle at between I and I plus 1. And as I go to infinity. So like they have to converge to 0, but obviously the distance of each one of them from 0 is at least 1. Is 1.
No, but they don't converge pointwise to 0 in the uniform topology.
well, why
no?
don't we do what I've done before, and let's just put a. I'll give you the standard example. I got confused about something when I was preparing this. There's a standard example showing that I don't want to waste time on this. There's a standard example showing that C of x is not a Banach space with a soup norm. You need to add functions which are, okay, sorry. This is, yeah, Manuel was right. So let's just remove this, and let's just change these heights. So the functions sort of look like that. So the functions fi look like this. They take values between 0 and 1. They're supported on a growing thing. And now take any function h, which is positive but tends to 0 at infinity. And then you're going to get that h times f, the pointwise product of h with f, tends to h in soup norm. But h is not compactly supported. Okay, so, oops. So I'll just think of there being another function in the background here. There's some function here that goes to 0, that's h. And then when you multiply these functions with each other, this product here, f1 truncates h here, f2 truncates h here, f3 truncates h here. And so these product, and there should be an I here. Okay, so these products, soup norm, converge to h. These products are these functions are compactly supported. This is the limit in soup norm, but this function is not compactly supported. Okay, so it's an easy example showing that this space is not a Banach space, at least if we take the soup norm. And for continuous functions, you sort of want to take the soup norm. For integration, you want to take the soup norm. Otherwise, integration won't be continuous. And so just a few more words about this. So again, for people who are interested in topology, basically what we're thinking of CCX as a union over K in X compact of continuous functions supported in K. And each of these we can equip with the soup norm, and it becomes a Banach space. It's its own Banach space because soup norm is these continuing functions are a complete space on a compact space with respect to the sup norm. And then when we take this union, we get what's called a direct limit. So CCX is a direct limit of Banach spaces, and with the direct limit topology, it becomes what's known as a locally convex topological vector space. So it's a vector space with a topology which is locally convex, and that's just a discussion for people who are interested in these things. Um, um, so now let's continue with the theorem. So let's move back to the theorem. I've explained the terms in the theorem, but I haven't explained why this is an important theorem. So this, there's an arrow here which takes a measure mu and defines the corresponding linear functional, and it's very easy to check that this, well, not, it's easy to check, maybe not very easy to check, let's remove the word easy. It's easy to check that if two measures are different, if they differ on a set of positive measure, then you can find a continuous function that tells them apart. So in other words, it's not hard to check that this mapping is injective. Different measures get sent to different linear functionals. And what's harder in the proof of this theorem is that this mapping is surjective. So in other words, whenever you define any continuous positive linear functional on this space, you've actually had to define a measure. Okay, so that's more the deeper content of this theorem. And let's write that as a separate corollary. Um, in order to define a Radon measure on X, suffices to define a continuous positive linear functional on CCX. Okay. Any questions about the Riesz representation theorem? We're going to be using it quite often to define measures. And later we're also, well, it can be used, I'm not sure we'll get there in this course, it can be used not only to define measures using the theorem, but also to define topologies on measures and to say what it means for a sequence of measures to converge. So that's also another situation where it's very useful to have this point of view. Here's another proposition that I won't be proving. If you look at continuous compactly supported functions on Rn, you get a collection which is dense in L1 of Rn. So this is something that we teach in real analysis here in Tel Aviv. So if you haven't seen the proof of this, this is nice to think about as an exercise. It's sort of not completely trivial, but it's not very hard. So I'm assuming this, but now I want to use the previous discussion and the Riesz representation theorem to show you the following corollary about the Siegel summation formula. So for any Radon measure mu on Xn, if the Siegel summation formula, I'll remind you what this formula says in a moment, holds for mu and for F compactly supported continuous, then it holds for all F in L1 and f hat belongs to L1 of mu. Okay, let's look at the Siegel summation formula and go back to this corollary. Where did this go? Here we are. So this is the Siegel summation formula. I'm taking functions defined on Rn. In the Siegel summation formula, I'm taking every function in L1, but in the corollary, I'm taking a subcollection of functions in L1, and these are the compactly supported continuous functions. Given the compactly supported continuous functions, I'm defining a new function on the space of lattices by summing the values on the non-zero integer vectors. Then I'm claiming that f hat is well defined, and I'm establishing this integral formula. Now, what I'm saying, this is part of the Siegel theorem that we'll be proving. Now, what I'm telling you using the Riesz representation theorem and the fact that compactly supported continuous functions are dense in L1, what I'm telling you is that if I define this formula only for functions which are continuous and compactly supported, so not for all functions, just for a subcollection of functions, and I verify this property, then everything written here for L1 is also true. Okay? So first of all, let's think about the first statement here, that this f hat is well defined. If f is just some function in L1, then we might worry about whether this sum converges and whether the limit function is a integrable function to make sense of this formula. If f is continuous and compactly supported, then this sum for any lattice is a finite sum, right? Because the lattice is discrete and the function has a compact support. So there are only finitely many elements of the lattice for which this sum is non-zero. So there's no issue of convergence. Moreover, it's very easy to check that using the Chaboty topology and the convergence criteria we developed for the Chaboty topology, it's very easy to check that, again, if f is continuous and compactly supported, then this function, as a function of the argument, of the function of the lattices, is a continuous function. Okay, so it's a measurable function. It may not be integrable, but it's at least a measurable function. Okay, so let me write that down. And then last thing I'm claiming is if you can establish this formula for compactly supported continuous functions, you get the same formula for L1 functions. Let me remind you before I prove it, why is this important? Let me remind you before I prove it that when we used this integral, we used it for f being the indicator of a ball. So it's not a continuous function. Okay, so we are interested in using this for discontinuous functions.
Sorry, there is a slight, I have some confusion about this argument. It's a purely formal confusion, but so the f hat is well defined for a compactly supported function. You have this integral formula, so you can extend it to L1. Why does it make the, but you're not saying that this sum you have above defines
that's part of
L1 function, because it seems to me that this defines that as a formal expression, this makes sense for
yeah. That's what you're saying. I'm about to talk about that. What you're saying is exactly part of the statement, which I'm not actually not proving, but I'll write it all down and you'll see. Okay, so let's move to the proof. Proof. So this is, as you anticipated, the proof will be missing a step, okay, which I'll leave to you, but let me at least make formal what I want to do. So I'm going to define two mappings on CCN. So phi will be CC of Rn. So C will be a mapping, phi will be a mapping from CC of Rn into L1 of the L1 functions on xn with respect to the measure mu, and psi will be a mapping from CC of Rn to the real numbers. And I'll define them in this way. F hat of L, I'll use the same formula that I had in the summation formula. That's a definition of F hat. Now it makes sense. So let's write this down. Note F hat, sorry, the sum in the definition of F hat converges because L is discrete and F is compactly supported. So the sum is finite. In other words, we're only summing finitely many non-zero entries. F hat is continuous as a function of L. Remember, we're using this Chaboty topology, so I'm sketching the proof of this without being too precise. So if B is a large ball properly containing the support of F, and Ln Lj, let's say Lj is a sequence of lattices converging to L in the Chaboty-Fell metric, then for all large enough J, and all X in B intersect L, there exists an Xj in Lj of intersect B. Xj tends to X, and the intersection of B with Lj is exactly these Xj's. And the sum and so the sum in definition of F hat of L, F hat of Lj is finite with a bound on the number of non-zero summands. Okay, so this is a little micro sketch which should be enough for you to fill in the details. So just think of, I'll just say in words what I'm trying to express here, and then you can think about why this is actually a proof later. So this is a sum. A priori, it's an infinite sum. For every fixed L, it's actually a finite sum. And now I'm claiming that as a function of L, it's continuous. So what does that mean? It means that if I have a sequence of like this, then the evaluation of F hat on Lj should converge to the evaluation of F hat on L. So this by continuity of F, whenever Xj converges to X, we also have, of course, that F of Xj converges to F of X by continuity. And if this sum were bounded, in other words, the number of elements in this sum were bounded independently of J, it would be clear that F hat of Lj converges to F hat of L. And I'm claiming that it is true that this sum is bounded by the number of non-zero elements, non-zero summands in this sum is bounded by a number independent of L, and that follows from the definition of the Chaboty-Fell metric. Okay, so I leave it to you to think about it. So the proof is sketched here. So now this function is well defined if F is compact and continuously supported, and it's f hat can be integrated. Of course, the integral of a continuous function, I never said that f hat is compactly supported. So the integral of a continuous function might not be finite, might not exist. But I'm assuming in the corollary that formula, Siegel summation formula, does hold for continuous compactly supported functions. So now let's use that hypothesis. And so we are assuming that the integral of f hat on xn with respect to this measure mu equals the integral of f with respect to vol for all f continuous and compactly supported on Rn. Sorry. My iPad has gone on strike here. All right. Okay, now let's compute some norms. So let's look at these two functionals here, and I want to use the fact that compactly supported continuous functions are dense in L1. So I want to show that these mappings are obviously linear mappings, and I want to show that these mappings are bounded with respect to the L1 norm on their so in other words, if I can bound the output, the right-hand side, in terms of the L1 norm of the left-hand side. And that's precisely the content of the Siegel summation formula. So let's start with phi. So the norm of phi of f, by definition, this is the L1 norm. Let me put in a bracket because this is a little bit confusing. I'll write everything down and then I will explain what I did. Okay, so I take a function f, which is continuous compactly supported. This whole line is for f continuous compactly supported on Rn. I take such a function, and I'm interested in the L1 norm of phi of f. Phi of f, just by definition, is this guy, this function f hat. So the L1 norm of f hat is just given by the formula. You take to figure out the L1 norm of a function, you take the function, you put it in absolute value, and you integrate over Rn. So that's just a definition of the L1 norm. And I'm saying that taking a function, taking its Siegel transform, in other words, this summation, and then taking the absolute value is bounded from above by taking the absolute values and doing the Siegel summation formula to them, right? Because that's just a triangle inequality in this sum. That's a finite sum, okay? So in other words, doing this and taking the absolute value gives you something smaller than sticking the absolute value inside. So that's what went into this inequality. So this is the Siegel summation of the absolute value, and by the Siegel summation formula, the absolute value is also a continuous function. So by the Siegel summation formula, we have this identity, and we get that the L1 norm of phi of f is less than or equal to the L1 norm of f. So that means, and let's now do a similar calculation for psi. So let me just write it out because I'm spending maybe too much time on this. So similarly, so I'll leave it to you to check. Psi of f is less than or equal to the L1 norm of f. And so this means that phi and psi are linear functionals on CCRN, which are L1 bounded. And since CCRN is dense in L1 Rn, there's a unique continuous extension of phi and psi to all f in L1. Okay, so let's scroll back up and look at what we're saying, what the corollary is, and what we've proved. Now we get exactly to Manuel's question. And so I used the fact that this holds for continuous functions, and now I'm claiming that everything in the formula holds for f in L1, and the corresponding function f hat is also in L1. And what I've found is that these two functionals can be extended, and they can be extended uniquely to all functions in L1 of Rn. So we've proved everything except that the same formula that we used in the definition, that this formula gives us the unique extension, okay, which was precisely what Manuel asked about. And this is the point that I'll leave to you as an exercise, so I'm not proving it. So it can be checked. Exercise that the extension of phi psi to L1 of Rn is given by the same formula. Okay, so that's what I wanted to say about. Yeah.
Can you? It's a
Sure.
bit embarrassing. I missed the definition of psi. Can you scroll up and say what it is, or just say what it is?
Where is it? Psi just takes the Siegel transform and evaluates its norm.
Okay.
Where did this go? Maybe I didn't write it. Did I not write it? I'm sorry. No, I guess I didn't write it, so it's no accident that you missed it. So thank you for pointing that out. So phi of f is f hat, psi of f is L1 norm of f hat. Thanks for the question. Okay. So now if we scroll back up to the Siegel summation formula that we're trying to prove, where did it go? Yeah, so what I'm saying now is we just need to check that this holds if we define f hat in this way for compactly supported continuous functions. Once we check that, then we will have this equality. This formula will make sense. In other words, it will define an L1 function. In other words, it will converge almost everywhere to some function f hat, and the function that it converges to will also satisfy this formula. Okay, so that's exactly what we're going to be doing when we prove this Siegel summation formula. We'll only prove it for compactly supported continuous functions, and then we'll use it for L1 functions, for general L1 functions. That's an important technical point in the proof. All right. So much for the use of the Riesz representation theorem in this. This is called the completion process or the extension process from compact supported continuous functions to L1 functions. Okay, now I want to also recall the Radon-Nikodym theorem that you probably know, but let me recall it anyway. I'm recalling it in our setup, which is Radon measures. So let mu1, mu2 be Radon measures on an LCSE space X. We say mu1 is absolutely continuous with respect to mu2, and we write this as follows. If whenever you have a set whose measure vanishes under mu2, then it also vanishes under mu1. And the Radon-Nikodym theorem says the following. If mu1, mu2 are as above, in other words, they're Radon measures on an LCSE space, on an LCSE space, then there exists a measurable function phi, non-negative, such that for every measurable set A, the integral, the measure of A with respect to mu1 is the integral with respect to mu2 of this function phi. And so phi is unique in the following sense. It's unique up to zero measure, i.e. if you have two functions, phi prime, and they both satisfy star, where this is star, then phi equals phi prime for mu2 almost every, this is an x. Phi of x equals phi prime of x for mu almost every x. And the notation okay. So this is the Radon-Nikodym theorem. Usually when it's taught in a measure theory course, again, we are doing things in a slightly different setting. So in the usual measure theory course, it's not taught as being taking place in an LCSE space, and the conditions on the measures are slightly different. They're assumed to be sigma finite measures. So it's not hard to check that on an LCSE space, Radon measures are sigma finite, simply because compact sets obtain finite measures in an LCSE space can be covered by countably many compact sets. And let me write down a special case of this Radon-Nikodym derivative, which is very important. So example, which sort of deserves its own separate discussion. This is the so-called Jacobian formula. So when x is Rn for some n, and mu1 is the volume measure, and G is an element of GL and R, mu2 of A is defined as mu1 of G inverse of A, then the Radon-Nikodym derivative d mu1 over d mu2 equals the absolute value of the determinant of G. Okay, so this is sometimes called the Jacobian formula. So in the case when you're applying a linear transformation, the Radon-Nikodym derivative is a constant function, and it's just equal to the determinant of this function G. And that's something that we're going to be using. It's kind of a standard fact. And now we get to groups. So maybe this is a good time to, yeah, so this is a good time to take another break. So let's take 10 more minutes and talk about measures on groups.
Barak,
Ken,
can I quickly ask
sure.
you, are you going to get to Siegel's theorem today, or do you expect to do this recap for the week?
Okay, let's continue. So now we're going to start thinking about groups and using groups. And so let me remind you what it means for a group to act on a space. So recall G is a group, X is a set, an action of G on X, notation G round arrow X is a map from G cross X to X. Notation, we just write it in this way, G next to X on the left. And this is called we can give this map a name, the action map, such that G1, G2X equals G1, G2X. And the identity doesn't move any point. Okay, so this is the definition of an action. As you remember, this is an element of X. So this is an element of X, and this is an element of X. So in this formula, we're applying the action map twice. In this formula, this product is an element of G, and we're applying the action map once. So it's slightly confusing notation, but it's very economical, and we get used to it. And we will work in a setup where in our setup, G and X will both be LCSC, which, as I said, I'm not defining if you don't know the definitions, but think about proper metric spaces. And the action map is required to be continuous. So this is where the topology enters into the discussion. This action map is continuous in both parameters. So in other words, if you have a sequence Gj tending to G infinity and you have a sequence Xj tending to X infinity, then Gj Xj has to tend to G infinity X infinity. It's sometimes it's stressed by saying it's jointly continuous. Okay, so that's the setup that we'll be interested in the main example. Take G to be GLNR for some large R or any closed. Well, let me first define the metric, and then we'll understand what closed means. The distance between G1 and G2 we can take to be the operator norm of the difference of G1 and G2, and that's putting a metric on GLNR. And this is now a nice LCSC group. Any closed with respect to this metric subgroup is LCSC. So when you have a LCSC space and you intersect it, with a closed subset, the topology on the closed subset is also LCSC. And again, if you don't know what LCSC is, just check it with a special case that I gave, which means it's a metric space where the closed balls are compact, and it's an easy check. So we'll be working with groups which are either GLNR itself or subgroups of GLNR, which are closed in with respect to this topology, okay? And with respect to this metric. And now that we have an action, we can talk about the action of, so if G acts on X, it also acts on Radon measures on X. And here's the formula. Okay, I'll write down everything and then I'll explain. Okay, so what I'm saying here is that you take a measure mu, which is radon on a space X, and you define a new measure, which is denoted by G star mu. It's called the push forward of mu by G. Maybe I'll write that down. G star mu is called the push forward. And it's defined by this formula, composition with the inverse. And you can check quite easily that this mapping takes Borel sets to Borel sets. That comes from the fact that the action is continuous. And so if A is a Borel set, so is G inverse of A. This then makes sense, and this defines a measure. And this measure is also Radon. So this is the action on measures. And it satisfies the action property. So in other words, if I do this twice with G1 and G2, that's why I put in the inverse here. If I use G1 star and multiplied by G2 star, and I use this formula, then putting in the inverse ensures that we get this axiom here also for the action of the group on the space of Radon measures. So this is the notion of action on the space. In terms of the Riesz representation theorem, RRT just is shorthand for Riesz representation theorem. The integral of f with respect to the push forward of mu is nothing but the integral of f composed with g. So f composed with g of x is f of gx. So it's not hard to check that this inverse on the level of sets translates to translating the argument without the inverse on the level of functions. So this is a different way to think about the same operation. Take functions, if you compose them with G, take continuous functions which are compactly supported. These functions are also continuous compactly supported. This formula defines a new measure. That measure is this measure, and this measure, it can also be described in terms of this formula. And so this is would be the definition, and the identity Yeah, the identity holds for all functions in L1. Once it holds for continuous functions, it holds for all functions in L1, and that's again by the same fact, the Riesz representation theorem. What happens to continuous functions uniquely determines what happens to all functions in general, or just completely describes the measure. Okay, so another definition, mu is G invariant if this happens. So we're going to be interested in G invariant measures on spaces. And the basic proposition, which is simple but very, very important, which I want to highlight, is the following. If you have an action of a group G on it, maybe I'll add a definition, sorry, of what a transitive action is. We already discussed this, but let me say it again. So the action of G on X is called transitive if for any x1 and x2 and x, there exists a G and G such that G of x1 is x2. And now if G is acting transitively on X, and you have two non-zero G invariant measures, everything is in the Radon category. Are proportional. I.e., if mu1, mu2 are both G invariant and Radon and non-zero, then there's a non-zero scalar, a positive scalar C, such that for all measurable sets A, the measure of A under mu1 is multiplied by C is the measure of A under mu2. Okay, so that's the proposition. So it's giving you a uniqueness property for invariant measures when the action of the group is transitive. Now, if the measure is finite, you can always remove this ambiguity of proportionality just by requiring that the measure is a probability measure, which means it assigns measure 1 to the entire space. But in the general case, measures don't have to be finite, and so we don't have a kind of a canonical proportionality, a canonical normalization. So we just use this equivalence relation of proportionality. Okay, what's the proof? This is, I'm going to be sketching this and leaving you a bit as a giving you to fill in the details in the exercise sheet for those of you who are doing the exercises. So we have two measures, mu1 and mu2, and they're both G invariant, and we want to show that they are proportional. So we'll work with the Radon-Nikodym derivative. Now, the Radon-Nikodym theorem assumes that mu1 is absolutely continuous with respect to mu2. So let's first assume that. So assume mu1 is absolutely continuous with respect to mu2, and let phi be the function, which is the Radon-Nikodym derivative of mu1 with respect to mu2. And so this is a function which is defined almost everywhere. And using the G invariance of mu1, mu2, one can show that phi is constant almost everywhere. So more precisely, after modifying phi on a subset of measure 0 with respect to mu2, phi is G invariant. It's a G invariant function. And this part is the fact that you can do this modification is an exercise. Once you know that, it's an exercise using basically the uniqueness of the Rado-Nikodym derivative. And once you know that, since we have transitivity, by transitivity, phi is constant, right? You have an invariant function, so it assumes the same value at x as at g of x for any g. But if you take x and apply all possible g's, you get all points in the space. So now phi is a constant, and therefore mu2 is C1 times U1, where C is the constant value of phi. So that solves the that proves a proposition, assuming this exercise and also assuming this absolute continuity. Now, what do you do if we don't have absolute continuity? If mu1 is not absolutely continuous with respect to mu2, define mu3 to be mu1 plus mu2. This is the usual trick that you learn in measure theory. So now mu3 is absolutely continuous. Sorry, the other way around. Mu1 and mu2 are both absolutely continuous with respect to mu3, right? Because if A is assigned 0 measure by this sum, then of course it's assigned 0 measure by each one of the mui's individually. So now mu1 is absolutely continuous with respect to mu3, and so is mu2. Now, if mu1 and mu2 are G invariant, then so is mu3. And so by the previous case, there exists constants C1, C2, such that mu3 equals C1 mu1 equals C2 mu2, and therefore mu1 mu2 are proportional. Okay, so that proves this proposition. So we'll be using this proposition, this uniqueness, over and over again. And let's do some examples so to make this less mysterious. Let's call it the 0th example is, oops. I'm having some trouble with my iPad and I don't know why, but okay. So let's talk about X being Rn and G being also equal to Rn, and G acts by translations. And so you all know from the first course in measure theory that the Lebesgue measure, which we're denoting by the volume, is the unique up to scaling G invariant. Borel measure on Rn. And if you look at your notebooks from your measure theory course, you'll note that the proof of this uniqueness really does use the local finiteness, or in other words, if you want this, the Radon property for the in order to get this uniqueness. Of course, you can always define a measure to be 0 on the empty set and infinity on every other set or other similar examples. So, but if you insist on local finiteness, then the Lebesgue measure is the only one, and the measure is usually formulated as the theorem is usually formulated as a uniqueness statement where the scaling is given to you. The scaling of, there's a natural scaling of the Lebesgue measure on Rn by the fact that the unit cube, say, has measure 1. So it's stated slightly differently, but this is the standard thing that's proved in a basic course on Lebesgue measure. The second example is somewhat similar, but slightly more complicated. So X is still Rn, and G is SL in R, and by matrices of determinant 1. And the action is by linear transformations. And so now this action is not transitive, but SL in R can map any non-zero vector to any other non-zero vector. And so that means that G is transitive on Rn minus 0. And of course, G also preserves the fixed point 0 and is transitive on 0. In other words, when G acts on Rn, there are exactly two orbits, 0 and everything else in the space. And there is a, we know that there is an invariant measure on each of these pieces on Rn minus 0. Can use the volume measure. We've pulled out the point at 0, but that's a point of 0 measure. So we can restrict Lebesgue measure to the complement of the point at 0, and that's an invariant measure for SL and R. And here we use the Jacobian rule. So by the Jacobian formula, since the determinant of elements in G have determinant 1, G preserves this measure. And on 0, we can take the delta function, the Dirac measure. And so this means that on all of Rn, any G invariant measure, of course, all the time I'm talking about Radon measures, any G invariant Radon measure on Rn is of the form C1 times the volume measure plus C2 times the Dirac measure. Okay, so these are the only two invariant measures for the SLNR action on Rn. Okay, now let's do a slightly more interesting example, which is SLNR acting on itself. So we saw in example 0 that Rn is acting on itself by translations. Any group can act on itself by multiplications, and in fact, it can act on itself in two different ways, by left multiplication and by right multiplication. We didn't have this distinction in this example because Rn is abelian. So translations, you can act by translations by adding on the left or adding on the right, and it doesn't matter. In a general group, the group is not necessarily abelian, so you have two actions. So G and any other group, G is now going to be SL and R, but this is a general comment. G, SL, and R. It's on itself, right? And I want to define them. So the left translation is multiplication on the left by G. The right translation is multiplying on the right by G. But if you want to make this an action, you stick in the inverse. So both of these will satisfy LG1 composed LG2 equals LG1 G2, RG1 composed with RG2 is RG1 G2. So both of these maps define actions, but if I want this formula, I should put in the inverse here. Okay, so what about measures on G which are invariant under the left action or under the right action? I'm just going to define one. This is, of course, part of a general theory. I'll say a few words about the general theory after defining it. So let's define an SLNR invariant measure on SLNR. So given a subset of SLNR, say a Borel subset, let's define curly C of A to be TA, where A is an A and T is between 0 and 1. So this is called the cone over A, even though it's strictly speaking, it's not really a cone. So let's draw a picture. So here is 0. 0 is not an element of SLNR. It's an element of, I think of the 0 matrix. It's a matrix in MNR. And SLNR is some kind of subset of MNR. It's the subset, it's the matrices in MNR with determinant 1. And then if I have some subset A of SLNR, I form the cone, which means I just connect the points in this subset to the identity, to the 0 by line segments. So this set is the cone over A, okay? As I said, it's the language of cones that we were using before. This would have to sort of extend to infinity here, which it doesn't, but sometimes it's still called a cone, okay? And I'm going to define a measure, and I'm going to use these letters for it, M of SLNR. M of SLNR of A is defined to be, okay, so let me, is defined in this way. So MNR, n by n matrices, real matrices, is obviously isomorphic to r to the n squared. It's the n squared dimensional Euclidean space because we have n squared matrix coefficients. And so we have a Lebesgue measure on Rn squared, which is denoted by vol. And this is what I mean on the right-hand side, okay? And on the left-hand side, I'm defining this measure. And again, I'm reminding you of my convention when I have, when I have a nice thing like a nice group and I use the letter M, this is supposed to be a particularly nice measure. So the reason it's going to be nice is that it's going to be invariant under both left and right translations. Let's check that. One more thing to note is that A, if I use this obvious measure, all of SLNR is sitting here as a subset of lower dimension. It's a codimension 1 manifold. So it obviously has measure 0. So you can't, there's no obvious way to restrict the measure on n by n matrices to get a nice measure on SLNR. You have to do something slightly more sophisticated, and that's why we do this cone procedure. So this is the definition. Let's check that it's right invariant and left invariant. So claim M SLNR is invariant. Sorry. Left and right translations of any element in SLNR. Let's prove this claim. So first, let's note that for any G in G, the cone um, note that if I define the cone as I did here, and then multiply all the elements of this cone on the left by G. So I'll write down a proof here and then erase it so the notes are nicer. So if I was to write a G here, which means to left translate this cone, that would write a G here. But multiplying by scalars commutes with linear transformations. And so the G would actually move in here. And this would give me the cone over G times A. So I'm erasing now because these are going to be the notes. So that gives me this formula. The G applied to the cone is the cone of the set where you left multiplied by G. And similarly, you get this identity in the same way. And so let's check how the left, so in order to now finish the proof, I want to check that, so suffices to show, so to prove the claim, suffices to show that for any, let's say S in MNR, Borel, the volume of a set doesn't change when we either left multiply it or right multiply it by an element of G, where G is an SLNR. So, and the reason for that is if you think about, so indeed, write a matrix we have a matrix with n columns, V1 up to Vn, and we just write that as a vector in this way. So if this is our way of identifying n by n matrices with vectors of size Rn squared, and we think about what the action of A of G is doing. So G acts in these coordinates, G acts on, let's write LG. Left multiplication by G acts on MNR by this matrix. G here, G here, G here, zeros everywhere else, right? Because when I left multiply, again, I'll use color and then erase the color. If I left multiply by G, then what I get is the matrix is acting separately on each column. And so if I'm writing things, if this is my first column, then basically I'm acting on V1 by multiplying it by G. So that's this block G here, zeros below the block. And similarly, all VI's get multiplied by G. So the matrix acting in these coordinates by left multiplication is just n copies of G in a diagonal matrix. And so the Jacobian of this mapping as a mapping from MNR to MNR is the determinant of G to the power n. but we are in SLNR, and so this is 1. And so that means that SLNR is preserving the volume measure on MNR, and we're getting this equality here. And if you think about right translations, you sort of do a similar trick, except you decompose your matrix into rows instead of columns, and change the parameterization, and then you'll get exactly the same action, but it'll be an action by right multiplication by the inverse of G. And again, it's the or if you like, it's the left multiplication by the inverse transpose of G. And again, using the fact that G has determinant 1, you get that right multiplication preserves the measure. So I won't do that in detail, but I'll just write it down. So similarly, RG preserves the volume measure on M and R, and hence preserves this measure. Okay, so what we found is that SLNR has a nice measure on it, which is left invariant and right invariant. And by the previous proposition, such a measure is unique up to scaling. And so a measure on a group which is invariant under multiplication is called a Haar measure. So this is the remark. So we found an example of a Haar measure. So if G is LCSC, it has a right Haar measure and a left Haar measure. Let's give these measures names because they're okay. So let's call this guy new right, and let's call this guy new left, and they are the unique up to proportionality measures on G, which are right and left invariant for any G and G. And so we know from the proposition that if they exist, they're unique. And then Haar was the one who proved that any LCSC group has a invariant measure like this. And we just proved that SLNR has an invariant measure like this. And in fact, for SLNR, it's the same measure. In the general case, there's no reason for it to be the same measure, which is both left and right invariant. If, so I'll write that down as a comment here. So if nu L equals nu R, again, up to, everything is only defined here up to proportionality. So it means we can find a constant multiple of nu L, which is equal to nu R. Then this is a property of the group, and it's an important property of the group. Then G is called unimodular. So we exhibited concretely a measure on SLNR, which is left and right invariant. Hence, this is Haar measure, and SLNR is unimodular. In the general case, it's not completely trivial to get a concrete formula for the Haar measure on a group. Depends on your group somehow. It's easier for these matrix groups or for Lie groups. It's more complicated for general LCSC groups, but we're not going to go there in this course. All I'm saying is that these measures always exist, and we just showed it in the case that interests us, which is SL and R. Okay, another case which is interesting for us.
Sorry, can I ask a quick question about this?
Sure. Yeah.
So in this case, like maybe maybe not quite a good question. In this case, epsilon r is it's a hypersurface in Rn squared. So we could.
Right. We use the fact we use that structure to define the. We use this hypersurface, so it's kind of a trick proof because it is a hypersurface. Correct.
Yes. So. So I was thinking, is there? Maybe I answered myself. In general, just the n-1 measure on a hypersurface is like the standard surface area would kind of.
No. That's not so easy as you might think. There is no standard surface area, so-called. To get a surface area measure, you need to have a notion, for example, of a Riemannian metric. So the way the general proof works is one of the ways the general proof works, for at least for Lie groups, is to define an invariant Riemannian metric. And once you have an invariant Riemannian metric, you can use it to define the analog of the surface area metric. Okay, but in general, if you take a general vector space and you, without a Riemannian structure, and you put in a codimension like a hypersurface, there's no obvious canonical way to restrict the measure to the hypersurface.
I guess kind of the obvious way would be to take the derivative of the volume of the cone, but then you might as well work the volume of the cone directly.
Right. But
Okay.
again, to take the derivative, to take the volume of the cone or the derivative of the volume of the cone, there needs to be a zero, which is sort of naturally placed. And okay, it's sort of a question of like, in which category you're working in, what's your obvious equivalence relation. I just want to sort of emphasize that in order to make this construction general, the way that's usually done is by talking about, there's an intermediate step which involves Riemannian metrics. So you take a group, say a Lie group. On a Lie group, before putting an invariant measure, you put an invariant Riemannian metric, and then you use that to define the measure. Okay. The same group can be embedded in SLNRs in different ways potentially. And you would worry that if you do things using one particular embedding, say the cone construction using one particular embedding or another, you might change the definition of your measure and so on. So, well, that can't happen because of the proposition, but it would be kind of strange if you were appealing to the uniqueness and also to one construction. So, okay. Yeah, okay, this is a philosophical discussion, so I'm not, I hope I have sort of answered it, but there's no obvious answer. Okay, so one more group that will play an important role, two more groups that I'm going to introduce two more groups that are going to play an important role and put Haar measures on them. And they are both semi-direct products. And so let's talk about the first one of them. So this is example 4, I think. Let me just, what's the numbering on our examples? Ooh, yeah, 4. So let's let U be G in SLNR so that G preserves E1. E1 is the first standard basis vector. So in terms of matrices, U looks like this. It has, on the first column, you have E1, because when you left multiply by this element, you have to preserve E1. And then you have something above and something below the lines. And so I'm just going to write A and X here, where A lives in SLN-1R. X is a general vector in Rn minus 1. Okay, so it's okay. So this should be clear that these are exactly the matrices that map E1 to itself and have determinant 1. The reason that this matrix has determinant 1 is because the entire matrix has determinant 1. So this is my group U, and I want to put a Haar measure on it. So the Haar measure on it is sort of defined in terms of a repeated integration or a Fubini-like formula. So here is the Haar measure. This group is also going to end up being unimodular. So the measure I'm about to define will be both left and right invariant. So, so just a moment. Sorry. All right, so I'm expressing this measure by, of course, the measure of a set should be the integral of its characteristic function. So this is the indicator function of S, and I'm integrating the indicator function of X by a repeated integration using these two coordinates in the formula for U. So on the X coordinate, I apply the volume measure in Rn minus 1, and on the A coordinate, I apply the Haar measure in SLN minus 1 that we defined in the previous example. So I'm claiming that this measure, so this measure mu is both left and right invariant. In order to check that, let's do a little calculation. Let's figure out the group law. So I'll do this quickly. What's the group law on U? So I want to think of AX, the pair AX, as representing the matrix that I wrote down before, 1, 0, X, A. And so let's compute A1, X1 multiplied by A2, X2 as elements of this group. So this just means I need to matrix multiply these two matrices. So when I do that, the 1 and the 0 remain because it's a group, and A1 and A2 just multiply in the usual way because this is matrix multiplication in blocks. And on the top part, what you're going to see is that X2, when I take a column here and I push it over here to do the multiplication, X2, the elements of X2 are going to touch this 1, and the elements of A2, the columns of this A2 are going to hit this X1. So this means that I'm going to get X1 plus X2, X2 I meant. Sorry. X2 by plus X1 times A, where this is right multiplication by A. Okay, and let's do the computation. So this is the same in the coordinates that we
You mean
are
X2
using.
plus
This is
X2 plus X1 A2?
yes, thank you. This is an A2. In the coordinates that we're using, it looks like that. Okay, these kinds of products are sometimes called semi-direct products. This is an example of a semi-direct product. Whenever you have, okay, let me just complete this computation, and maybe next week I'll say a few words about semi-direct products. So let's check that this is indeed left and right invariant. So integral, I'll write this quickly since we're sort of short on time here. And I'm using these coordinates. So this is supposed to be, sorry. Okay, I'm sorry. I'm running low on time, and I will make a mess of this. So but it's not worth spending time on today. So what I'll do is I'll just add this to the notes after today's lecture. So let me just, since this is on video, so this is to be added to the notes. You'll see it posted in the notes. And let me just say one more word about another example, and then you'll see the proofs in the notes. So this is going to be a unimodular group with this definition. This definition will give us both a left and right invariant metric. Another example is this very similar looking group. Okay, so it's very similar, except the ones and the zeros are in different places. But if you work out the multiplication rule, so it looks like this. And here the action on the, let's think about this. So here the action on the X looks like A1, X2 plus X1, if I didn't make a mistake. And this group has a name. This is it's called ASL n-1R. It's the affine group. And this group is, we'll say more about this group. It's also an important group. And this group is also unimodular with the same measure. So you just take the same measure I've defined up here by this repeated integration right here. Instead of looking at matrices which have 1 here and zeros here, think of matrices which have the 1 and the 0 as they do over here, but use the exact same formula, and the computation will show that this group is also unimodular. So I'm going to put the details of that in the notes. And so all told, we have 3 examples of unimodular groups with their Haar measures, SLNR, U, and this group ASLN. Okay, that's it for today. And I'll see you all next week.
תודה, להתראות.
בבקשה, בבקשה.
תודה רבה. תודה.